This is 2018 USA JMO problem number 3. Here is a view of this problem. We are given a cyclic quadrilateral ABCD, and we're also told that the diagonals of this cyclic quadrilateral meet at a 90-degree angle here. Let E and F be the reflections of D across BA and BC. So let's go ahead and draw these reflection lines. So we draw a perpendicular to AB. We measure this distance, so probably somewhere here. So this is E, the point E, but it's really the reflection of D, right? So that I don't forget, so let's just write it as D prime. So this is a 90-degree angle here, and let's call this foot of this altitude as X, let's say, right? So dx is equal to xe, right? So let's make note of that before we forget it. And we are also told to do the same thing, so we will reflect across CB. So it will be something like that, I guess. So that's F, and again, this is another reflection of D. Let's call it D double prime, and because of this reflection property, so first of all, this is 90 degree, and secondly, if you call this point as Y, dy is equal to yf. So the notation that I employ in this problem is again following Evan Chan's post on AOPS forum. And now let's continue. We have the point P, which is the intersection of BD and EF. Yes. BD and EF, that's pretty ugly, but we can do it, I guess. So something like that. So if I just may, okay, so something like this. So we have, this is the point P here, the intersection of BD and EF, and suppose that the circumcircle of EP D, okay, this is ever harder to draw all these circles and stuff, but yeah, so it's probably something like that, I would say. There you go. Yeah, I'm not very concerned with drawing it very accurate, but so that's the idea. And in a similar way, oh, and this point here is Q, by the way. We label it as Q, and in a similar way we draw the circumcircle of FPD, and we let it intersect the circle omega at D and R, so at the point R basically. So FPD would be so something like that. Don't worry too much about drawing the circles very accurately, but okay, so this point here is R. Obviously these two green circles, they meet at P, and P is on DB. It's the intersection of DB and EF as well. Now finally we need to show that EQ is equal to FR. So let's go ahead and try to EQ FR. Okay, so it's not very clear in this picture. Obviously it's not up to scale, so but we need to show that these two red lines are congruent. Okay, right. Okay, so let's go ahead and, well, I can just keep the red marker. So we did introduce some notation. I would like to introduce one more notation here in line with Evan Chan's solution. So call this point as Z. Now, if you focus your attention on triangle ABC, and omega would be the circumcircle of that triangle ABC, and D, the point D, is on the circle of triangle ABC, right? So notice that D is on the circumcircle of triangle ABC, and as such I can go ahead and notice that from the point D, which is on the circumcircle of ABC, we drop 3 perpendiculars to the 3 sides of triangle ABC, right? From point D, we drop a perpendicular to AB. The foot is X. The foot, when you draw the perpendicular from D to BC, is Y. And similarly, if you drop a perpendicular from D to AC, that would be Z. But by Simpson line theorem, right, by Simpson theorem, X, Y, Z are collinear, right? So therefore, Simpson line, applying Simpson theorem on triangle ABC with point D on the circumcircle, that would give us, implies that X, Y, Z are collinear. Okay, so this is a very well known by Simpson line theorem. Okay, so now focus your attention closely on triangle. Oh my god, I just spit it on my screen. Oh. Okay, anyhow, yeah, focus your attention on triangle DEF, please. D here, EF. Do you guys agree that X and Y are the midpoints of the respective segments, sides DE and DF on that triangle DEF? As such, XY is the midline, but we are told earlier that XYZ are collinear. Let's go ahead and, before I forget, let me draw that line. So we have XYZ collinear. Second of all, dx is equal to xe, dy is equal to yf. So these are both midlines, suggesting that dz would be equal to zp. Do you guys see that? If you don't, just focus on triangle DEP now, DEP, and we know that, well, first of all, we know that XY is parallel to EF, right? Because again, it's the midline. XY is the midline of triangle EDF, and as such, it is parallel. And now you have a parallel line. Consider triangle DEP. On triangle DEP, X is the midpoint, so let me just do another sketch here. So you have this triangle DEP, you have this point X here, you have a line which is parallel to the other one. Obviously, it forces this other point Z to be parallel, to be the midpoint as well. If X is a midpoint, Z would be the midpoint of DP. So that's perfect. So this is midpoint. But then the implication will be amazing. So from the point B, you can interpret the point Z as the foot of the altitude from B to side AC on triangle ABC. And secondly, you extend that BZ beyond Z, beyond the foot of the altitude. It hits the circumcircle at D, at this point D, and we know very well that DZ equal to ZP implies that P is a special point on this triangle. Do you guys agree that this is the altitude, this is the ortho center of triangle ABC, right? Does that make sense? So I don't know how to put that, but P, so this is orthocenter. I just proved it, right? So P is orthocenter of triangle ABC, simply because PZ is equal to ZD, where well, obviously BZ is an altitude, BZ altitude, and further you extend BZ to hit and BZ intersection the circumcircle of ABC being equal to D, and combining it with this thing, right, implies that P is the orthocenter. Okay, so if this is confusing to some of you, that's perfectly fine. Let me just quickly draw a new sketch over here just to summarize what we did so far. So if you have, what I'm saying is, consider this triangle ABC. We have an altitude here. So the foot of the altitude, we mentioned it as Z. And so this point here is D. And we have this other point here, the point P. And we are told that the PZ is equal to ZD, right? It is, I claim that this is a very well-known property, that P would have to be the the ortho center of triangle ABC. You can more or less, I mean, you can prove it in various ways. This is mainly an angle chasing type of argument, and you can establish that, for instance, if let's do this one, I guess. If you connect these two, you can establish that well, because these two are equal, PZ is equal to ZD, and this is a 90-degree angle. These two angles are congruent angles. And second of all, because this angle ACD subtends this minor arc AD, it's equal to this angle over here. right? And that would suggest that so it forces this angle to be 90 degrees as well, forcing the point P to be an ortho center. All right, so we have established that P is the ortho center of triangle ABC. Now the last part of the problem, we will be using phantom points. Let's go ahead and extend. Obviously, my picture sucks, but if you extend, let's see if I can use any other color. Let's use gray. Okay, extend a CP to meet this picture is really bad. So extend it to meet the circle at this point Q prime. Okay, so when we extend it to meet at this point Q, yeah, why not? Okay, so let's extend it to meet at this point Q prime. Let's focus on what's happening here. So do you guys, I think everybody agrees that BA is a perpendicular bisector of DE, right? This is by definition because E is a reflection of the point D across AB. So therefore AB bisects DE, but moreover it is perpendicular to it as well. So AB is a perpendicular bisector to DE. I claim that it is also, AB is also a perpendicular bisector to PQ prime as well. Can you see that? Well, it is obvious, right, from the from this lemma, call it, that I have just proven. Notice that P is the orthocenter. As a result, CP is the altitude of triangle ABC. So this is a 90-degree angle here. And because P is the orthocenter, if you call this point something, let's call it K, you just realize that PK is equal to KQ prime. Does that make sense? They have to be because of that lemma. So as a result, AB also bisects PQ prime. So AB bisects DE, AB bisects PQ prime, and moreover, DE and PQ prime are both perpendicular to AB, so therefore they are also parallel. So in that sense, DPQ prime E is a trapezoid, but more than that, it is an isosceles trapezoid, right? So therefore, so let's write that down here maybe. DPQ prime E isosceles, and I love isosceles trapezoids. Why is that? Because they are cyclic and cyclic. All right, so that's amazing. All right, so DPQ prime E isosceles trapezoid. Furthermore, DPQ prime E cyclic. Hey, DPQ prime E cyclic means Q prime is on the circle DPE. Use the other three labels, right? So it's on circle DPE, but moreover, by definition, Q prime is also on omega, right? All we did was to extend CP to meet circumcircle of ABCD at Q prime. So can you see another point which is on both of these circles? Of course. What is that? The point Q. And that's exactly why I named it Q prime, the extension, right? So this implies that Q prime is indeed nothing but Q. So therefore, I'll try my best not to ruin my picture, but I'll make a small change in my picture. So let's redraw this picture slightly, if you don't mind. Okay, so there you go. So therefore, my initial drawing was really a bad one. The true drawing should rather go like that. Does that make sense? Oops. So maybe I can go like, I don't know. I can revise my circle a little bit. Okay, so that's a horrible circle, but you get the idea, right? So this point here is the point Q, and Q is on CP, right? Does that make sense? I hope so, right? So that's an amazing revelation, right? So, but then we're almost done now. So this further will imply that because we have an isosceles trapezoid, QE is equal to DP, right? So let me rewrite that. So this segment, which we are very fond of and we are really interested in measuring, right? Because of this. So EQ, this implies EQ is simply equal to DP. Now, of course, you know where this proof is going, right? So we have just shown that this red segment is equal to dP Now you can pause the video and you can try to see how in the world we can prove dp, because EQ, we need to show EQ is equal to FR, right? Hey, EQ is equal to DP. Can I just show that FR is also equal to DP using pretty much the same tools? Of course. All we do, guess what? The same analogy, just extend AP, let it hit the circumcircle, this time at point R prime, and just show that R prime and R are indeed congruent because as it turns out, DP Q, let's write that, because DP R prime F is again an isosceles trapezoid, and boom, so it is cyclic because it's isosceles trapezoids. Isosceles trapezoids are cyclic, right? So dp r prime f, hey, r prime, it means is on the circumcircle of dpf, right? Hey, r prime is also by definition on omega. I know another point which is on both of these circles, and this is the point R. Hey, I can redraw my picture as a result, right? So oh shoot, I don't like this business, people. Okay, so let's just do it because we are so close to finishing this. I will try my best. So I'll just redraw the circle more like this. Pretend this is a circle. I know this is not the best circle, but there you go. Call it R now. I no longer need to call it R prime or something the same way for this one. Well, okay, let's just keep it for the thingy. Okay, so, and that's it. So we have, therefore, what we proved is that, come on. Okay, there you go. So we have just shown that because it's an isosceles trapezoid, we have just shown, so this implies that indeed FR is simply equal to DP. Hey, that pretty much does the thing, right? FR is equal to DP, EQ is equal to DP, so therefore FR and EQ are equal to each other. So combine these two results, EQ is equal to DP. Oh my god, that's a P. Therefore, and well, this DP is also equal to FR, suggesting that EQ and FR are congruent, and that solves this JMO problem number 3. Hope to see you guys in the next lecture, where we go over the second day's Usajmo problem solutions.